So let's go. Improper integrals. Okay, so before going to improper integrals, I need to review of L'Hopital's rule. So a quick review on L'Hopital's rule. Okay, so what does L'Hopital's rule say? Is that if f of a over g of a is equal to either 0 over 0 or infinity over infinity, okay, then the limit as x approaches a of f of x over g of x is the same thing as the limit as x approaches a of f prime of x over g prime of x. Okay, so that's L'Hopital's rule. Okay, so in other words, if when you want to find a limit, you get one of these two undetermined forms, okay, so 0 over 0 or infinity over infinity, well, you could evaluate the limit directly, or you could just do the derivative of the top and the derivative of the bottom and then do limit. Okay, let's do a few examples. So this is more of a calculus 1 concept, but it's good to review it because we're going to need it in improper integrals. So for example, let's start with an easy one. Limit as x approaches 1 of x squared minus 1 over, I don't know, x2 plus 2x minus 3. Okay, that's a very easy one. So I see that I have 0 over 0. If you plug in 1, you get 0 over 0. So I could apply L'Hopital's rule. And when I apply L'Hopital's rule, over the equal, I'm going to put a little h or something, just to explain that from here to here, I applied L'Hopital's rule. Okay, and so the derivative of the top is, of course, 2x, and the derivative of the bottom is 2x plus 2. And now I replace 1 inside, I get 2 over 4, so I get 1/2. And that's my answer. Okay, that's one way to evaluate a limit instead of what you could have, what you would have regularly done, which would be to factor the top, factor the bottom, and cross out an x minus 1. Okay, that's another option. Okay, any questions?
Do you mind repeating it again?
No, I don't mind. Okay, so L'Hopital's rule, what it says is that if when I have an undetermined form of the form 0 over 0 or infinity over infinity, I'm allowed to just derive the top, derive the bottom, and then do the limit. Okay, so in this case, I put in 1 inside, I get 0. I put 1 on the bottom, I get 0. So I'm going to apply L'Hopital's rule, which is to derive the top and derive the bottom. So the derivative of top is 2x, right? The derivative of x2 is 2x. And then the derivative of the bottom is 2x plus 2. Okay, so that's what I did. Here I applied L'Hopital's rule. I did f prime over g prime. Derivative of top over derivative of bottom. And that is 2x over 2x plus 2. And now I replace the 1 inside and see what happens. So I get 2 over 4, it's a half. Is that okay?
Yeah.
Okay, let's do a few more.
Sir, there's someone in the waiting room.
Oh, thank you. Okay, let's try another one. Limit x approaches 0, sine x minus x over tan x minus x. Okay, so here's another one. So the first thing I do, of course, I check if I get one of these two undetermined forms. So if I plug in 0 on top, I get 0, 0 on the bottom, I get 0, so I could apply L'Hopital's rule right away. Okay, and what do I get? What do I get? Can you tell me? Cos x minus 1 over secant squared x minus 1, right? The derivative of secant, of tangent is secant squared. And now what? I replace 0 inside again. What do I get? The cosine of 0 is 1, 1 minus 1 is 0, secant of 0 is 1, 1 minus 1 is 0 again. So I need to do L'Hopital's rule again. Equals, I use L'Hopital's rule.
Sir,
Yes?
there's somebody in the waiting room.
Thank you. Okay, so let's do again the derivative. Derivative of cosine is negative sine. And the derivative of the denominator, so secant squared will be 2 secant times the derivative of secant, which is secant times tangent. Okay, so let's, at this point, maybe it's a good idea to start simplifying things. So I'm not going to do L'Hopital's rule here, I'm just going to write equals limit as x approaches 0, and here I have, so negative sine x times, on the bottom, I mean, over 2 times secant squared x times tangent, but tangent is sine x over cos x. Okay, and I could do limit x approaches 0, so the cosine I'm going to send upstairs, and I'm going to get negative, and the signs will cancel. I will have negative cos x over 2 times secant squared x. And then if I plug in 0 inside, cos of 0 is 1, secant of 0 is 1, and so my answer is negative 1/2. Try this one now. The limit as x approaches 0, e power x minus e power minus x minus 2 sine x over x sine x. Okay, so the first thing I do, I plug in 0, so I get 1 minus 1 is 0, minus 2 times sine of 0, which is 0, so I have 0 on top, and on the bottom, 0 times 0 is 0. So I will do L'Hopital's rule right away. Limit as x approaches 0, so derivative of e to the x is e to the x, minus derivative of e to the minus x is negative e to the minus x, so this becomes a plus, and then minus 2 times cos of x. And on the bottom, I do the derivative of x sine x. Don't forget there is a product rule here, so 1 times sine x plus x cos x. This is my first step using L'Hopital's rule. Let's plug in 0 again, so I get 1 plus 1 is 2, minus 2 times 1 is 0, and on the bottom I have 0 plus 0, again 0. So 0 over 0, I do L'Hopital's rule again. Derivative of the top, e to the x minus e to the minus x, and then plus 2 sine x. And then on the bottom, I have to do derive, I have to derive again, so I get cos x plus, so product rule here, 1 cos x minus x sine x. Okay, and I plug in 0 again, I get 1 minus 1 is 0, plus 0 is 0 on top, and on the bottom I get cos of 0 is 1, cos of 0 is 1, so I get 2 minus 0, I get 2. So I get 0 over 2, and so my answer is 0. Perfect. So an improper integral is a definite integral that has one or both of its bounds infinite, or for which the integrand, you know what the integrand is? It's what you integrate. Has a vertical asymptote. Okay, so I'm going to explain you what that is. So there are two types, okay? Two types of improper integrals. Type 1. You have a situation like this. Either you have from a to infinity, Okay, so this pen is starting to dry up. Try another one. Okay, or from negative infinity to A, or from negative infinity to infinity. Okay, so there are three cases. Basically, remember that the integral, the definite integral represents an area. Okay, so the first area would be something like this. So I don't care what the function looks like, but I'm interested in the area from a certain value A until infinity. So as you see, the area is now open. It's an open area. Okay, because the upper bound of my integral is infinity. Second case would be, of course, the other side. So my function, let's say, is like this, who cares? And from negative infinity until A. Okay, that's also an improper integral because one of the bounds, the lower bound in this case, is negative infinity, it's infinite. Okay? Okay, one of its, or both of its bounds are infinite. The last case is if both the bounds are infinite, so it would be a case like this. Let's say, okay, and I'm looking for the total area from negative infinity to infinity. These are the first type of improper integral. Okay, improper integral is where one of the bounds is infinite. Okay, or also you could have a case like this, still in the first type, a situation like this where you have from A to B, okay, of f of x dx, except that the function has an asymptote at A or B. So let's say something like this. There's an asymptote here. This is A, this is B, and I'm looking for this area. This is also a type 1 because there's a problem at one of the bounds or at both bounds. Okay, any questions? Okay, type 2, and then we're going to start solving some of them. Okay, we're going to start to evaluate. Type 2, okay, is when there's no problem at the bounds. Okay, but somewhere in between there's a problem. Okay, so for example like this. So let's say there is a vertical asymptote somewhere here, and I'm going from A to B, and this is my situation, let's say. Okay. I'm looking for this area. And this is a tricky one, because sometimes you won't notice that there is a problem in the middle. Okay, so now there's some added complexity, because before I would give you a definite integral, find the integral. This you know how to do with the fundamental theorem of calculus, right? F of B minus F of A. But now there's an extra step you have to do, and you have to ask yourself, is b defined for all values between a and b? Okay, we'll do examples, and you're going to see it's not that complicated. Okay, so again, two types of improper integrals. First type is when one of the bounds or both bounds are either infinite or the function goes to infinity there, or minus infinity. That's the first case, type 1. Type 2, the function is well defined at a and b, there's no problem, but somewhere between a and b, there's a place where the function goes to infinity. Okay, so when there's situations like this, we have to treat these definite integrals a bit differently. Okay, not much. Okay, it's almost the same thing. But there's an extra thing I have to point out here. So let's start with a simple example. Okay, so example here. The integral from, let's say, 1 to infinity of 1 over x2 dx. Okay, so here's an example. So obviously this is an improper integral because one of the bounds is infinite. Okay, and what's important here is the notation. Look at how I'm going to write this. I'm going to write the integral from 1 until t, I'm going to call this t, of this 1 over x2 dx, and then the t, I'm going to take the limit as t approaches infinity. Okay, so this basically means the exact same thing. Instead of putting infinity, I put a t and I make t go to infinity. But why do I do this? Because now this t is not infinite anymore, it's an actual number. I could treat this as a regular definite integral. So I'll treat this as a regular integral, fix it, evaluate it, and once I'm done, I will make t go to infinity. Okay, so equals limit t approaches infinity, and the antiderivative of 1 over x2 is, I think, negative 1 over x. We should know this by now. And we evaluate this from 1 to t. Okay? And so this is equal to limit as t approaches infinity, so you plug in t inside, so negative 1 over t, minus, plug in 1 inside, so negative 1 over 1. And now I have to evaluate a limit. So the limit as t approaches infinity of 1 over t, that's 0. And so my answer is 1. Easy enough? Okay, so we write the integral from 1 to infinity 1 over x2 dx. So how do we write this? We write converges to 1. Converges to 1. In other words, the function 1 over x2 is something like this. That's what it is. That's what it looks like. Okay, and there's also on the other side. Obviously there also, but what this tells me is that this area here, this region, is getting closer and closer to 1. The further you go along the x, the closer this area becomes to 1. Okay, so we're going to talk about convergence much more when we're going to do sequences and series. But for now, keep in mind that it means that the bigger the x is, the bigger the t actually, from 1 to t, this is 1. So the bigger the t, the area from 1 to t under the curve 1 over x2 is getting closer and closer to 1. Okay? That's what it means that's what I mean when I say converges to 1. Any questions?
Yeah, sir, I don't get what converges means.
What converges means?
Yeah.
Okay, what converges means, it means that if you find the area from 1 to 2, okay, so let's say you put a 2 here, well, you will get you'll get a half. You get 1 minus 1/2, you get this area is 1/2. You understand?
Yeah.
What I just said? Okay, if you go to 3, let's say, okay, so if you go 1 to 3, when you plug in 3 here, you'll get 1 minus, you get 2/3. If you go to 10, okay, if the area from 1 to 10, you'll get 1 minus 1 over 10, you'll get 9 over 10, the area. The further you go on the t, if you do t is a million, you'll get 1 minus 1 over a million. You understand? You get 0.999999. And the bigger the t, of course, this is going to be very narrow, the closer this area will get to 1. If you take t equals 20 billion, you will get the area will be 0.999999999 and so on. That's what it means converges to 1.
Okay.
Okay, good. Okay, let's try another one. So the integral from 0 to 1 over x dx. So of course the problem is at 0, so I'm going to write equals limit as t approaches 0 from t to 1 over x dx. That's what you did? Okay, the only thing is that my function is between 0 and 1, so I'm approaching 0 from the plus side. That's important, I have to write this. So I have to put a little plus, okay? Because my function is like this. One, 0. So my t is approaching 0 from the plus side. Okay, that's why I'm putting a 0 plus. Okay, because of course that's my region. Okay, and then we do improper integrals as usual, definite integral as usual, I mean. So limit t approaches 0 plus. The antiderivative of 1 over x is, I hope you are good with this, ln x, evaluated from t to 1. And so if you plug in 1 here, you get ln of 1 minus ln, I forgot to put limit, sorry, minus limit as t approaches 0 from the plus side of ln of t. This is 0 minus, and ln of 0 is negative infinity, so minus negative infinity, and so I get infinity. So this region here goes to infinity. This one converges to 1, this one goes to infinity.
Can you explain that last part again? Where you
The
got the t from the 0 plus, and you got that to infinity?
This here?
Yeah. Is that because of the, like it went up into infinity on the graph?
Because I'm sorry, because?
Because it went up into infinity on the graph.
I'm sorry, I can't hear you well.
Is it because it went up into infinity on the graph, since we were dragging it from the plus side?
Well, here also went to infinity. It goes to infinity, but that's not why. It's just that it seems that here, in this case, this function is not getting close to the axis fast enough. Okay.
Okay.
The closer, if you take 0.00001 until 1 and you find this area, you're going to get very big. And the closer you get to 0, the bigger it gets the area.
Okay.
So we say that the integral from 0 to 1 of 1 over x dx. So if it goes to infinity, we say, so in this case it converges to 1. In this case, we're going to say it diverges. So here we go. 2 little questions, quick one, okay, and I'm going to correct them right away. So that you have them as examples. So let's say from negative infinity until positive infinity, e negative x dx, that's one. And the other one, I'm going to do the integral from, let's say, negative 1 until 1 of 1 over x dx. Okay, so here's 2 examples. So the first one, obviously this is a type 1 improper integral. At the bounds I have problems. So what do I do in this case? Okay, so this is my function. Okay, I'm not expecting you to draw it, but at least know that we're looking for the whole area here. From minus infinity until positive. That's what I'm looking for. So in this case, where both bounds have problems, then you have to separate the integral in 2. So I want to go from negative infinity to something, plus from that same thing until positive infinity. Okay? Where do I take, which number I take? Anything you want. I would take something very simple. I would take 0, because that's an easy number. Okay? So basically what I'm doing is I'm separating the region into 2 parts. Okay, from negative infinity to 0, and then from 0 to infinity, and I'm adding the 2 areas. And now this becomes 2 exact same problems as the one we just did. So we're going to limit as t approaches negative infinity of the integral from t until 0 e negative x dx, plus limit, so let's say let's call this u approaches infinity from 0 to u e to the negative x dx. Okay, so this is equal to limit t approaches negative infinity. The antiderivative of e to the negative x is negative e to the negative x, evaluated from t to 0. Plus, and here I'm going to have limit as u approaches infinity of negative e to the negative x from 0 to u. Okay, so if I plug in 0 inside, I get negative 1, minus, if you plug in minus infinity up here, you will get infinity. So that's what I get. Plus, if you plug in infinity here, you will get 0, minus, if you plug in 1, you get minus 1. Okay, so I get minus 1 plus infinity minus plus 1, so I'm going to get infinity. And so my integral diverges here. Okay, now this one is trickier. Because this one, if I plug in 1, I have no problem. And if I plug in -1, I have no problem. Okay, we're out of time, so I'm just going to do it fast. Okay, so at -1, there's no problem. At 1, there's no problem, but between -1 and 1, there is 0, and at 0, there's a problem. Okay, so this function has a problem at 0. So I need to rewrite it as -1 until 0, because there's a problem there. And then 0 to 1. Okay, my function looks like this. I think you know what 1 over x looks like. Okay, so basically I'm looking from -1 to 1. That's the region. And that's it. This becomes now 2 type 1 improper integral. Okay, so this integral here is a type 2. And this becomes 2 type 1s now. Okay, so let's do it. Limit when t approaches 0 from the left side. The integral from -1 to t 1 over x dx plus limit as u approaches 0 from the right side, the integral from u to 1 over x dx. And that this becomes so limit t approaches 0 from the left side, ln x minus ln of 1 and then plus ln of 1 minus limit u approaches 0 plus of ln of x. Okay, and if you do this, you will get negative infinity. This is 0, this is 0, and you'll get plus infinity. So I get negative infinity plus infinity. What is that? I don't know what that is. That's infinity. Okay, you cannot say that it's 0. Okay, they don't cancel out, so it still diverges. Okay, so at any point when you evaluate, you get an infinity that appears, you have a divergent integral.